Yeah.
Wow, good crowd. Welcome everyone. I'm Allison Rickmore. I'm Stanley's PhD advisor, and I will also be for his dissertation defense in the Department of Mechanical Engineering here at Stanford. Often I show slides with embarrassing pictures of people before thesis defenses, but Andrew should be relieved that I didn't actually have time to put together embarrassing pictures today. But I do want to say a few words about Andrew and the great experience I had working with him at the time here in the Charm Lab at Stanford. When Andrew first joined the lab, it was very practical. Like, so, what's going to happen, why, and make a plan. And I actually feel like it took some convincing for me to convince him to do the PhD, because he really wanted to make sure that he was going to do something that was really going to contribute to the world and prepare him well for a future career and lifelong happiness and success. It's a tall order, but I'm really glad that I convinced him that with a PhD, he would both have a lot of fun doing cool things in the research lab and making discoveries, but that would also prepare him very well for a successful life. And I've really enjoyed working with Andrew over this time. He has gotten to work in industry a couple of times and do internships, and is one of many of my students who have super attractive companies always saying, "Can you come do an internship again?" Because of all the great things that he contributes. But also, he's been a wonderful contributor to the life of the laboratory, and always there as a very supportive friend and colleague to folks in the research lab. And we are going to miss him very much when he graduates. I will give the caveat that he's probably defending his PhD thesis a little earlier than he would otherwise, and that's my fault because I'm going to Japan next quarter, so we will have him for a whole additional quarter after he does his defense. And so we're lucky during that time to have him as a running partner, as someone who will always want to turn the temperature down, whereas people want to turn the temperature up in the lab. And then also as someone who's always a good sounding board and who's doing some very interesting and novel and creative work in haptics. And so, Andrew, I want to thank you in advance for giving the presentation, to all of your friends and colleagues who have come, and then also to Andrew's family who has joined us for this event. So, you take it away.
Thank you very much for the introduction, Allison. Today the title of my talk will be Haptic Jamming, Controllable Mechanical Properties and Shape-Changing User Interface. So before I jump into the content of my research, I want to give a little bit of a background in haptics for anyone here who might not be familiar. In the context that you hear it in most these days, it's probably in terms of cell phones. When we had smartphones that came with touchscreens that no longer had buttons, commercial companies have done a lot of work to try to add the haptics or the touch feedback back to smartphones to make it feel like you're pressing a button and by stimulating your sense of touch with vibrations. But in the haptics research lab, we think of vibrations as only one method of haptic feedback that's kind of one-dimensional and lacks some of the richness of other forms of haptic feedback. So here, for example, we have a commercial interface called the Phantom Omni, which is a kinesthetic haptic device. And the idea here is it's basically just a little tabletop robot that the user can hold onto the end effector and move the end effector around in space. And as they move this end effector around in space, you can render a virtual environment on a computer screen and have the cursor on that screen follow the motion of the user as they're moving this little robot around. And this transmits not only the motion signals, but force signals back from the virtual environment, so that if this cursor runs into, say, the side of a teapot, you can use the motors inside of this device to render torques that the user will feel as forces as though they're pressing against the teapot, even though this end effector is still just in the air. So the original goal of this project was working on a grant for medical simulation and trying to improve the haptic feedback in medical simulation. And if we look at what exists currently in medical simulation, there's kind of two ends of the spectrum. There's this side where it's very reprogrammable with these haptic force feedback devices. And the advantage here is that you can really change what you're showing to the user dynamically. And on the other side of the spectrum, we have mannequins, which are very physical. You can get your hands all over But the downside there is that once you practice on one mannequin, it's hard to change that mannequin to do something else. So we really ask the question whether we can have the best of both worlds here. Can we have a device that can physically recreate to be a bunch of different objects with different mechanical properties, but still have to be something that the user can touch directly with their hands rather than through a single point through a tool, as would be the case with a kinesthetic haptic interface like this. So some background, we're not the first people to ask this question. Typically, shape-changing user interfaces, a common implementation is through a pin array. So in this case, you have a lot of pins, in some cases hundreds of pins, that are all separately actuated to recreate shapes that the user can then touch directly with their hands. Another approach to this is more of a deformable crust, where rather than actuating from underneath, you have actuation within the crust so that it can kind of deform to change shape. There are also tactile displays that focus less on changing shape and more on changing the mechanical properties that the user feels when they touch it. For example, electrorheological fluids and magnetorheological fluids, or applying an electronic or magnetic field, will change the mechanical properties. Or balloon, kind of pneumatic arrays, or electromagnets. But when we started this project, we were inspired by what at the time was pretty recent. Particle jamming was becoming quite popular in robotics. And particle jamming is a technology where if you have a flexible membrane and you fill it with a granular material, normally it's very soft and pliable, you can deform it very easily. But if you apply a vacuum or suck the air out of that membrane, the granules will kind of jam together and become more rigid. So using that method, you can control the mechanical properties of this interface that you're doing. This was applied to things like a universal gripper that could basically pick anything up by becoming rigid after you form it around an object, or a manipulator, or a user interface for robotic locomotion. So here's a video of an early prototype that we came up with a tactile display using particle jamming. And we have separate cells here that are all silicone membranes filled actually with coffee ground. There have been a number of studies from other universities showing kind of the benefits and drawbacks of different types of granular material. They've shown that coffee grounds actually work quite well, that they can display a big range of stiffnesses, potentially because of the irregularity of the shapes of the granules help them lock together when you apply a vacuum. So we lay this whole kind of thin membrane on top of an air chamber where we can control the pressure. And depending on which cells are soft and which cells are rigid, when we increase the pressure from underneath, the surface will kind of deform into different shapes. And you can see that when we vacuum certain cells, they become a little bit darker as the coffee becomes denser. So it makes it easy to see which cells are soft and which cells are rigid. So I'm going to give a brief outline of the content of my talk today. I'm going to first talk about the design and testing of these novel haptic interfaces that we call haptic jamming surfaces. And then I'm going to talk about the mechanical modeling of what the user actually feels when they interact with this device. And then I'm going to discuss the dynamic simulation of these surfaces to figure out what kind of shapes we can create. And finally end with control of actual devices to create those shapes. So here's a schematic of kind of what was going on in that prototype that I just showed the video of. This is a sideways cutaway view. So there's kind of two layers of silicone here on top of this air chamber, and we have air pressure through a pressure regulator, basically pumping air into this chamber underneath it to balloon the surface as we desire. And then the vacuum lines, if these are dark, they're jammed rigid, and when they become light, it is no longer vacuum, they become soft. So the air pressure then pushes that part of the surface upwards. And you can combine multiple cells to create lumps of different sizes. And here we have air cylinders that we're using to pin the nodes in between the cells. And to explain why we need to pin the nodes, I have this schematic here. You can see that even though these three cells are all jammed rigid, you still have some silicone at the interfaces between the cells that can allow the cells to rotate about one another. So to really get the degree of freedom of shape control that we want, we had to add into some node pinning into this device. So in this case, you can keep the jam cells basically flat, and you can use the air pressure to balloon up the unjammed cells without things rotating about one another. So a little bit of what goes into building these silicone membranes and these haptic jamming cells. We make the membranes out of two separate pieces of silicone that we pour into these custom acrylic molds that we made on the laser cutter. And then we connect them using a stretchable silicone adhesive so that we can keep the two pieces together even as it's ballooning flattening out. And then we fill it with coffee and connect a separate vacuum line and an air pressure line into the chamber underneath it. And the vacuum line runs up through the chamber into the bottom of the cell. And then one thing we did with a student that I mentored for one summer, Adam Jenico, was running a perceptual study to see, basically trying to figure out what the user actually feels when they're touching these devices and how much you have to adjust the vacuum levels or the air chamber pressure to really get a noticeable effect. So using these psychometric curves, we can figure out what we call the just noticeable difference, which is basically how much you have to change the vacuum level or the air pressure for the user to just be able to barely notice that you changed something about the device and what they're feeling. So that gives us a better idea of when we're controlling these for a user interface, exactly how much we need to adjust those parameters. So moving our design from the single cell to multi-cell array, as I mentioned, we had to include node pinning, and you can see in these silicon molds I've embedded some hex nuts that we can then screw into from below, and then we glue these hex nuts in between the two layers of the silicon. And these air cylinders, basically when they're pressurized from the top, they'll push the piston down, that will pull down on the node and keep it into that height. And moving on to larger arrays, for this one we were really focusing on seeing how compact we could make this device. And for these molds, we actually tried out embedded vacuum lines. So rather than having tubes coming out of the bottom, these ones were embedded into the silicone, which, while functional, was extremely difficult to assemble. It required kind of more complex molds, but we did show that it was feasible to still get controllable vacuum in all of the different regions. So here you can see which the darker ones are jammed rigid and the lighter ones are still soft. And this whole device is now only about 1.5 inches tall. We also changed the node pinning mechanism for this device as well. As I mentioned in the 4-cell array, we were using air cylinders, and the downside there is that it's really just an on or an off switch. It's either pinned all the way down or it's released to move freely. And with this device that one of our rotating students, Mark Sauer, came with the original idea for, we're using a reel that kind of wraps around this, or sorry, a string that wraps around this reel and a little solenoid that's embedded into the wall of the box that can either extend into or retract from the reel. And I'm just going to jump to the video since this diagram is a little complicated to see. So you can see that the solenoid is down here, and when it extends into this reel, you can no longer pull on the line. But when the solenoid retracts, the reel can spin freely, and there's a little constant force torsional spring that applies just a minimal amount of force to reel the line back in so that it's not pulling too hard on the surface. And then we attach it to a little binding post that's embedded into the silicon. And so using these methods, we can create a variety of different shapes with just a 12-cell array. And here we have a video. So for example, this node is pinned, and this node is free to move. Basically different sequences of chamber pressurization, node pinning, and cell jamming can create a variety of different shapes. So now that we have this device design, we've done some preliminary testing, we really wanted to dive deeper into the mechanical modeling of what exactly the user is going to be feeling when they're interacting with this device, when they're pressing on with their finger. So to do this, we have this setup here with a Phantom Premium and a force sensor on the end, and we 3D printed this little nub on the end that's about the size of a finger. And we ran a couple of tests here. The first one, we actually supported the cell from beneath by acrylic. So we're really just looking at the compression of the granules and trying to model these force displacement curves. And there's a couple of interesting things. So we have displacement on the x-axis and force on the y-axis here. And you can see that the dark lines are during the compression and the dotted lines are during the rebound. And this is for increasing levels of vacuum applied to the cells. And there's a couple interesting things to note here. The first is that there's a lot of hysteresis in these curves coming from the plastic deformation as the granules shift around. And the other thing is that the stiffness is not linear. And we hypothesized after reading some of the literature on there's a lot of models out there of jamming materials at the very kind of inner particle level. And while we were focusing on kind of the more macroscopic level, what the user is feeling when they're pressing it, a lot of these models look at individual granules and how they slide against each other and the friction. And so from that literature, we found some papers that show that there are actually force chains that develop as you press on these sets of granules. there will be only certain granules that have the force, or that kind of absorb some of the force going through them. And these force chains, as you press harder, start to slide against each other and rearrange into shorter chains, making it stiffer as you compress further. And so for that reason, well, here's the model we developed. We needed the damper in series to provide that hysteresis into the curve, and we have a nonlinear stiffness of the spring in series. And the total displacement x is going to be the displacement, or the change in length of that spring, which is x1, and the change in length in the damper x2. And these aren't real things that are actually happening in the device. There's no spring and damper in the granules. These are just kind of imaginary variables that we use for the model. So we really want to combine these two equations to get rid of x1 and x2, since there's no way to measure this parameter. So when you combine these two equations, you get this equation here. And if you look at the fact that we have a time history of data here from our force displacement curves, we can model this as an over-constrained system in matrix form, where the pseudo-inverse of f times x provides the least square solution for this constant matrix C, which allows us to find the best fit for the stiffness parameter as well as the damping parameter in this model. So we ran this model. You can see kind of a MATLAB simulation of what's going on with our actual data as well as what's going on in our model. And we ran this for a variety of stiffness values, or for vacuum levels here. You can see qualitatively from these plots that the model fits the data fairly well. But another thing that we can do to kind of double check our model is look, instead of solving for the displacement, we can solve in terms of the force. And unfortunately, this is not a linear equation, so we can't use the same method to optimize for K and B. But we can take the K and B that we solved for in the displacement model and plug it into the force model, just kind of as like a double check for how well our model holds up. And you can see the green lines here still qualitatively fits the data quite well. So looking at how those parameters K and B change with vacuum level, you can see that they increase. This is the vacuum level on the x-axis, and stiffness and damping on the y-axis. Those increase as you increase the vacuum level. And looking at our errors here, you can see that when there's no vacuum applied, this model actually has a little bit of error. If we go back to the curve, you can see that on the curve with no vacuum. But as soon as you apply any vacuum at all, pretty much the error goes way down and the model fits a lot better. So that was, as I mentioned, with acrylic underneath the cell. And when we set it up in our haptic jamming device, we usually have air underneath the cell, so it's not supported. And that makes the model a little bit more complicated because the whole cell can bend, and then you also have, if you push too hard, the cell just completely yields. And you can see that in our force displacement curves here, where eventually we get to this yield force, or yield stress, and then eventually, at a certain point, you're just stretching the silicone at the bottom after the granules have totally yielded. So we added the silicone as a spring in parallel with this model, and ran some tests on empty silicone cells to see what kind of forces we were getting out of the silicone, and then subtract that out of the model just to then be able to use the same methods we used before to fit the stiffness and damping parameters to this unsupported cell by running the data up until before it yields. And we ran this for 3 cell sizes, the 1-inch, 1.5-inch, and 2-inch diameter cells. And again, you can see for each one we have slightly different stiffness and damping parameters in our model, but they all increase with increasing levels of vacuum. And here we have, again, the error showing that the model fits quite well. So now that we have a pretty good understanding of what the user is feeling when they touch this device and what kind of mechanical properties we can display, we wanted to move ahead and see what kind of shapes we could display. So we mentioned there that we have control both over the mechanical properties and the shape. So now we're moving on to shape simulation. And in our early conference paper, we've done some studies with single cells, just varying levels of pressure underneath them. And this study showed essentially what you'd expect out of a cell ballooning. As you increase the chamber pressure, it starts to balloon and become have higher curvature. But how do we know what's going to happen when you have multiple cells together and you have nodes being thin and cells being jammed? It becomes a much more complicated problem. So we looked to the computer graphics field actually to try to help solve this problem. And there are a couple of common methods for deformable body modeling. The most common are finite element analysis and spring mass models. And they both have kind of their benefits and drawbacks. The big benefits of a finite element being that they've been shown to be a little bit more accurate, although they're much harder to solve for and get the models to converge. We ended up going with the spring mass model because it was unclear whether this finite element model would actually provide an accurate model for a system with granular material involved, and all these nonlinear elements. Finite element models are based more in continuum mechanics, and that's kind of a different system here. So we're using C++ with Chai3D as a wrapper for the graphics, and we needed to be able to add node pinning, chamber pressurization, and cell jamming to this model. So we arranged these. Each circle here is a point mass in our array, and the yellow ones are the nodes in between the cells, the green ones are the boundaries between the cells, the blue ones are the cell interiors, and the red nodes are fixed at the edge. So between each node we have a spring as well as a damper, and you can solve for the acceleration of each point mass and each time step basically by summing all these spring and damper forces with gravity and then integrating twice to get position. And these methods are not new. We're just kind of creating a model that's kind of custom to our device so that we can use that model to study our device. So to accomplish the first of our actuation methods, to pin a node, we simply fix it in space by not updating the position after each time step when we're integrating all the other nodes. To model a chamber pressure, we looked at the point of interest that we want to apply a force to, as well as the 4 neighboring points in the grid mesh. And by taking the cross product of the vector from the left to the right node and the cross product of the vector from the node below to the node above, if you take the cross product in this direction, it will always give you normal going out from the surface, which we then normalize and multiply by the gauge pressure that we have in our simulation at that time step times the average surface area per point in the surface. And so qualitatively, you can see that our normal estimation works a little bit better than just having the pressure go straight up. And finally, we needed to model cell jamming. And to do this, we first thought, oh, maybe we could just increase the stiffness of the springs and dampers, because that's what our mechanical model showed. But really, we needed to increase the cell bending stiffness. And those normal springs would only kind of, if you increase the stiffness a lot, would always want to hold it flat. And we wanted our simulation to be able to jam a cell in any configuration and to be able to hold that shape in any configuration. So to do this, we looked at our point of interest as well as the point before and after it along each axis of the mesh. And if you imagine as this axis of the mesh is bending, you can calculate the angle that it's creating by taking the arc cosine of the dot product, of the normalized dot product of these of the two vectors. And I'm not going to talk too much about the vector map here, but ideally you want to apply a torque coming out of the plane to kind of make it bend back to its equilibrium angle. But since this is the point mass, we can't apply torque. So what we do is we apply forces to the points neighboring it, and then we apply a force to that point itself to balance out the forces so that you don't have the whole thing accelerating as you increase the torsional stiffness. And then we can update our equilibrium angles as the simulation is moving, and then when we jam the cell, we set its current equilibrium angle as the new equilibrium angle and keep it there so that it'll maintain that shape rigidly. So you can see qualitatively in this demonstration here that we can pin the nodes, unpin them. We made the cells turn a little bit darker when we jam them so you can see what's going on. So this cell is unjammed and these ones hold their flat shape rigidly, but we can also jam them in different configurations. So these ones are all now jammed in that balloon configuration. As we increase the pressure further, the unjammed cell balloons out, whereas the jammed cells stay rigid. So we have this simulator, but we wanted to be able to fit the parameters from that dynamic model to our actual device. So we used the Microsoft Kinect to collect surface height data to do this. So basically what we did is we just incremented the pressure underneath the surface with everything unpinned and everything unjammed, and basically just took data of how high the center of the surface had risen. And then to get our mass parameter from our model, we could basically just look at the zero crossing point of this curve. So at the beginning, it's kind of sagging under its own weight, and when you reach a certain pressure, you know how much force you're applying to the surface to just keep it level, and that gives you your mass parameter for your simulation. And to figure out the normal stiffnesses, basically the slope of this curve will either steepen or flatten depending on how stiff you make the springs. So we can run the simulation, basically a simulation of this test with a variety of spring stiffnesses, and we use a modified version of the bisection method where we basically just guess at first what we think the spring stiffness will be, and then we take a step size and adjust it towards what we see from our data. And we just iterate through this with smaller step sizes until we converge within what we see as an adequate step size. So that gives us our normal stiffnesses, and then we can do a similar thing for the torsional stiffnesses of the point masses, where we start with everything jammed and flat, and we just increase the pressure, and use the same method to figure out the stiffnesses that we need to apply to our torsional spring. So to verify that our model then actually fits the surface itself, we ran a sequence of actuations here that included a variety of node pinning and chamber pressurization and cell jamming. And these are photos of the actual device at those stages. And then this is data that we collected from the Microsoft Kinect showing the surface. And you can see the data is a little bit noisy, but it matches what our simulator output within the accuracy of the Kinect. So now that we have a model saying, given these actuation sequences, this is the shape that you're going to get, we kind of wanted to turn that around and say, if we have a desired shape, what are the sequences of actuations that we would have to put into the device to get that shape? So to test this out, we started with some topographical maps. And basically, by taking the hue channel of these images, we can get 3D surface data that we can then input as a desired shape into our device. And this is kind of a challenging problem because there's a lot of nonlinear dynamics, and it's very configuration dependent or non-holonomic in that. Depending on the sequence of your actuations, the same actuations in different orders will have greatly different results. So the algorithm we came up with looks kind of complicated on paper, so I'm just going to explain it with this video since it's pretty straightforward in concept. So this is our desired shape kind of input into the simulator. And then what we do is we just start from a unactuated array, and as it's ballooning up incrementally, we just pin each node whenever it reaches the height of the corresponding node in the desired data, and we jam a cell if it ever reaches the corresponding curvature from that same cell in the desired data. So some results. So this is our constructed data from the image. And for a 3x4 cell array, this is our input data. And our output data looks kind of like a mechanically filtered version of that doesn't really look anything like Australia. But if we slowly increase the number of cells in the simulator, we can see that as you get to larger and larger arrays, eventually it starts to resemble the input. And some other surfaces show some limitations of our device. This is the San Francisco Bay Area. You can see that even for the 9x12 simulator, it doesn't do a great job, especially because at the edge you have some high peaks, but we can't have high peaks output from our device because everything is fixed at the edge. In addition, these sharp peaks are very difficult to display with this kind of surface. To evaluate this more quantitatively, we use Pearson's correlation coefficient, which basically evaluates how well the input and the output match each other. And we can plot these for a bunch of array sizes that we tested. And as you would expect, as you increase the number of cells in the array, the correlation coefficient goes up. But what's interesting about this result is that it's not completely monotonic. You can see that there are occasions where, as you increase the number of cells, the correlation coefficient actually goes down. And we hypothesize that this is because if you have like a sharp valley in your desired image, if it happens to match up very nicely with a node in one array configuration, then maybe as you increase the size, it'll move away from that node. There is some potential there for certain applications where you could try to optimize this for certain images. So our device is what we call a 2.5D device. It's not truly three-dimensional, even though it can create surfaces with all 3 dimensions, and that you can't create something that you can really wrap your hands all the way around, and you can't create overhanging surfaces. So we use the terminology 2.5D to describe such a surface. So if we wanted to recreate 3D objects as accurately as we can, what we do is this technique called Z-buffering, where we look at the model from above and we color all of the surfaces based off of their Z height. So you can see that the higher it is, the higher intensity in this image. which we can then convert into this 2.5D data for our input, and then run it through our simulator and get that shape that was the output. So for example, we have a pineapple here that was the desired surface, and then it'll run the algorithm and try to match it as closely as it can. This is for a 5x8 array. And what we've noticed is that even if you have huge arrays, there are some shapes that are still not at all recognizable. I think some people have guessed that this looks like a frog. I've heard other things, but actually this is a bicycle. And you probably could have guessed that the bicycle is not going to work so well, whereas something like a pear would probably work a lot better. You get much higher correlation coefficients. So we can kind of intuitively, qualitatively guess which shapes are going to render well and which ones are not going to render well. But we asked whether there was a more quantitative way that we could do this before having to run the simulator for all of these values to get these correlation coefficients. So the method we came up with, we first started by thinking, oh, maybe the gradient will work, that'll give you the slopes. But for something like a pear that has very high slopes at the edge, that's actually not that difficult for us to render. What you actually need is the Laplacian, which is the second derivative, which gives you the changes in slopes. And you can see now that the pear, if you take the Laplacian of that input image, the pear has very low intensities and the bicycle has rather high intensities. And something like the San Francisco Bay, where we have features running off the edge, we can set the outer boundaries of the image to be 0 outside of our image, and then when you slide this filter kernel across it, that'll give you very high intensities of Laplacian at the edge. And this fit very well. We can see that our coefficient of determination for how well the Laplacian fits the output correlation coefficient is very high. And another knob that we can kind of turn when we're running this is with our filter kernel that we're sliding across the image to take the Laplacian, you can adjust this alpha value. And that basically tells you how much weight you're giving to the diagonals versus the vertical and horizontal axes of that filter kernel. What we found is that alpha value actually has very little effect on the coefficient of determination. So that gave us pretty good insight in terms of what shapes we could create. So then we asked the question as well, how do we go about actually creating these shapes and creating demonstrations that are both interesting and useful using this haptic jamming methodology. And I mentioned at the beginning of our talk that the grant that originally funded this project was for medical simulation, and we worked in collaboration with this company called Intelligent Automation Incorporated, and they built this big robot called the kinesthetic system for medical simulation, or Kinesys Medicine. And what you have here is a platform that's basically driven in parallel by all these motors with cables attached to it. And we add hand tracking so that the user stands next to this and looks down at this computer monitor that has 3D visualization. And as they reach the different areas of the workspace, this platform will actually move to that area of the workspace. And then we can put our display on top of it so that it changes shapes and mechanical properties as you reach that area of the workspace to match what you're seeing on the screen above it. So to do that, we needed to first automate our device, and this included adding like a pressure regulator and an electronic valve so that the whole thing could be run from the robot computer automatically. And then the resulting demo that we did was using just a single cell device. Basically, as you're tracking the hand and the platform is moving around, if it reaches an area of the workspace where we have like a lump shown, it will change into a rigid lump. If you move somewhere else, it'll go back to being a flat, soft surface. And this is just kind of like a proof of concept demonstration that we use. In this plot, we have seconds on the x-axis, and on the top plot, we have the position of the hand is the thin line, and the actual robot is the thick line. So you can see that the robot is basically following the hand around. And then when it gets within this region of interest, we inflate the cell and then jam it until the robot leaves that region of interest. But what we found is that the dynamics of this robot and our device were kind of limiting the immersiveness of this display. And especially with the kind of increasing popularity of head-mounted displays at the time, we thought it was really unnecessary to have this huge robot with a screen. And rather than trying to move it around, where the user never like totally gets over the illusion of this thing moving around underneath them, it's hard to do like a big continuous surface. So rather than focusing on this robot, we switched over to trying to get better control of our device for multi-cell arrays to just have this stationary device that we have sitting on the table that we can control the shape and mechanical properties very well. So to do that, we needed to close the loop on the shape output. To use that, we use the Microsoft Kinect here, mounted above the surface. And so this is a control block diagram. So we have our desired surface input, and for this 12-cell array, we use the dynamic simulator to show us some shapes that we at least thought were feasible to recreate. And then we have our surface output, which we can measure through the Kinect, and both of our desired shape and our depth image, we can calculate the cell heights or the node heights and the cell curvatures, and take the difference of these node heights and cell curvatures and plug them into that haptic jamming algorithm that I showed before. This gives you the nodes you need to pin, the cells you need to jam, and the air pressure that you need to set inside of the chamber. And we have a little inner control loop here where we just have a flow regulator with a PID controller. That basically takes the pressure setting and uses the pressure sensor and the flow regulator to make sure that the pressure inside of the chamber is actually at the setting that we wanted. So now that we have our 3 actuation inputs, they just go through the device dynamics and you get the surface output. Sorry. So here we ran it for 3 different surfaces on our 12-cell array, and these were all surfaces that we generated from our dynamic simulator that showed us that at least it was somewhat feasible to recreate these surfaces. So that helps us evaluate whether our closed loop control is actually working. And you can see this is running at 8 times speed, and the main reason for that is that for this first implementation we were using MATLAB for all the image processing and kinetic data. So that was kind of slowing down the loop rate quite a bit. But you can see we still get pretty good qualitative match here, for at least for these surfaces where we know it's feasible to recreate them. But if we move on to objects that aren't necessarily feasible for the surface to recreate, for example, this little rubber ducky, you can see that with only 12 cells, you have very limited resolution, and the output really doesn't look that much like a duck. But our simulator seems to show that if we make the array a lot bigger, we can get an output that at least resembles a duck. So this plot here, we have basically the pressure. So this is as you're moving through the control algorithm, you're increasing the pressure, and the correlation coefficient goes up, and the average surface area goes down to within the resolution of the Kinect. And then for the duck, as I mentioned, the 12-cell doesn't really look much like a duck, but with our simulated 100-cell output, you can start to see the simulated output matching the input of that duck. And some researchers like to say that the problem with simulations is that they're doomed to succeed. And apparently my advisor falls into that camp because she encouraged me to build a 100-cell array to verify that the simulation actually works. So I need to thank Kenji Hata for helping me pour these silicone molds and put coffee inside and work on the design with me. And we had to make some design changes as we were building this 100-cell array to make sure that it was a lot more robust. The 12-cell would function, but every now and then something wouldn't work too well. And we just imagine if you have hundreds of components, chances of all of those things working in unison are rather slim unless we improve our design. So here we have some binding posts that you can see there are these little slits in them, so that when we're pouring the silicone, it actually fully surrounds the binding posts rather than just having us glue them in on top, so that no matter how hard you tug on this thing, it's not going to just like stretch the silicone and slip out. It's actually fully embedded in the silicone. And then these are the tubes that we have little air filters on the end, so that when you apply the vacuum to these cells, you're not sucking coffee out of the cells. And then to control the electronics, we have a couple hundred, actually, or close to a couple hundred actuators here. So we use a daisy chain of shift registers, so that with just 3 outputs from our microcontroller, we can nearly simultaneously control all of these actuators for cell jamming and node pinning. You can see in this video, despite the fact that we have so many actuators and just 3 outputs from our microcontroller, we can have simultaneous control over all of the cells in this array. And you can see as the cells get darker, that's because they're jamming to become more rigid. And this is it running a little bit faster. At this point, we're running at the loop rate of our Kinect, which we moved to C++. So this gives you a sense of how much faster our control can be with C++ rather than MATLAB, as well as the fact that the device dynamics for vacuuming are not the limiting factor in terms of how fast the response we're getting in our control. And even when you increase the pressure underneath it and balloon the whole thing up, this can become quite large. So that the footprint of this thing, each cell is 1.5 inches, so the whole thing is 15 by 15. If you come by the lab later, I can show you a demo in person. You can see we still have control over all the vacuum levels as we go through that again. And going back to improving robustness, had a lot of work from Rob Pereira, Rowan Kona, and Elliot Hawks trying to redesign our node pinning mechanism, not only to be more robust than the solenoid pinning, but also this gives us truly continuous resolution rather than having the discrete teeth on the ratchet that the solenoid is sticking into. And so what we have here is a DC motor mounted with a little cam here, and as this cam rotates into the string, the advantage of using a cam here is that as soon as the teeth of the cam engage, this profile here is designed such that pulling up on the string will engage the cam further and tighten its grip on this string. So rather than using the motor to pull on the string, we can use the mechanism to kind of support it, and we're using the motor as what we call more of an activator in the sense that it'll change the result of the work that we do with the pneumatic actuator, but we're not actually doing any external work on the system itself with that motor. So I need to thank Robert and Rohan again for all the work they did assembling these devices. And one unexpected outcome of my PhD is I got quite a bit better at soldering. And yeah, there's just a lot of things that go into the assembly of this device. And here we have a video demonstrating the node pinning mechanism. So right now all of these are locked. So you can see as I tug on the vented screw that screws into the bottom of the surface, it won't move, but when we release it, it will be free to move. And then basically switching the direction of the bottom half and alternating with the top half. Now the bottom half will be pinned and the top half will be free to move. So we have 81 nodes in our 100-cell array. So we have 81 motors and 100 vacuum valves. So just some more photos of kind of what's going on under the hood. You can see this design got a little bit complex. If we really wanted to move it up to manufacturability at scale, we'd have to make quite a few other design changes because you've really got a ton of tubing and wires crossing here. But as a result, here's the depth that we'd simulated earlier. And now as we use our closed-loop control at the Connect, we have our Connect surface data here. And you can see that the output data is now actually starting to resemble our simulated output, unlike that 3x4 array that we showed earlier. And then we also built a custom graphical user interface. And I need to thank Joey Greer for helping me get the Connect integrated with this. And you can individually click on any of the actuators, or you can choose from a subset of pre-programmed shapes. Then as you run the algorithm, you'll see in the Connect data, you can see everything kind of actuating here, and then it slowly starts to match your desired shape. And then here's the bunny that I showed on my title slide, actually created on our 100-cell array. So that concludes the content of my slide. I just want to do a quick review of contributions before I move on to our future work. So we devised and realized a novel methodology for simultaneously controlling shape and mechanical properties of a tactile user interface. We formulated real logical models of a user interaction force with particle jamming interfaces from a macroscopic level. We developed and validated the shape control algorithm using a custom deformable body simulator of a haptic jamming surface. And we demonstrated closed-loop control on a particle jamming device. So expanding a little bit to where we see this going in the future, we've done some work with one of our rotating students, Nathan, trying to, as I mentioned before, this is really kind of a 2.5D surface. But ideally, we could convert this into a truly 3D surface. So for example, in this interface, we've taken 2 active jamming cells and kind of glued them together in the pattern of like the seams of a baseball. And you have, it'll start as like a soft kind of deformable baseball, and you can put it inside of other shapes and increase the pressure to balloon to fill up that shape and then jam it. And then what results is you can, with this one device, create rigid objects in a variety of shapes. But to create kind of a more automatic shape-changing device, Elliot has invented some high-strain actuators that we can embed inside of a cube, for example. And Margaret has done a lot of work kind of taking my dynamic model and moving it to 3D so that we can see with this cube interface, these are now not using a mold. We can just kind of automatically have it change into these shapes. And this shows promise that our deformable body methods will continue to provide insight into what shapes we can create even at the three-dimensional level. So there are a lot of acknowledgments people I need to acknowledge to thank for all their help with this work. Of course, my advisor, Allison, who's been there to direct this research from the beginning and provide support throughout. Not only as she mentioned, convincing me to stay for the PhD and providing a really cool project for me to work on, but encouraging me through the hard times and being enthusiastic during the high times. And my reading committee, Dr. Mark Kokoski and Sean Fulmer, as Mark was technically my academic grandfather, if you look at those terms, as he was Allison's advisor when she was a graduate student at Stanford. And Sean and Dr. Jonathan Fan, we collaborated a little bit on as I mentioned, with these 3D surfaces, kind of looking at a vision to not only have it be a shape output, but use some stretchable sensors that Jonathan Fan is trying to develop in his lab that have this be both a computer output and a computer input. So you can imagine if, say, currently now you have someone using a CAD model on their computer and they click print and send the object to the 3D printer. Well, if you have these embedded sensors and a really 3D object that can change shape, you just click print, it would change shape. And then if you don't like what something looks like, you can kind of just press in it, or press that dimension into it, and then send it back to your CAD, and that'll be reflected in your model. So I have to thank John Fan and Sean Fulmer and Elliot and Allison for really helping us think of this vision. And then finally, Dr. Doug James, who really helped us respond to some reviewers for our journal article on the graphics side of things. And I also need to thank the Charm Lab. You guys have been not only extremely supportive in terms of helping with research and everything like that, but you guys have really become some of my closest friends along the way. And I really appreciate, it's you guys that really makes it fun to come into lab every day and really gets you out of bed in the morning. I need to thank my undergrad advisor, Dr. Catherine Kuchenbecker, who got me interested in haptics in the first place and really mentored me in applying to PhD programs in the Haptics lab back at Penn. And my Stanford alumni mentor, Steve Herrick, who's been supportive throughout. And I also need to thank my family. My mom, Barbara, my dad, Richard, my sister, Jessica. You guys have obviously, that's it, been there since the beginning and been super supportive along the way. My girlfriend, Kristen, who supported me through some major endeavors these past few months, and I really appreciate that you've been there for me and that you're here today. And finally, I need to acknowledge all my other friends, in particular the triathlon team. You guys have provided another dimension to my life, and it's just been such a great experience at Stanford because of all of you guys. And with that, I'll open up for questions.
For anyone who hasn't been on a thesis discussion before, we have open questions from the audience, and then after that, we'll do a closed session where it gets to be filled by a committee. But for now, anyone is welcome.
Were the motors that were getting the notes, was there like a location feedback, or how were you determining whether or not those the notes actually been by the motor, whether or not the motor?
So that we have a little bit of work to do to change the circuit since we originally designed it for the solenoid pinning array. So basically, we only have this on or off control. Basically, if we want to pin a node, we turn the motor all the way on, and then once it makes contact, the upward force on the string will kind of pull the cam mechanism to engage further. Then if we turn it on, we basically just turn it all the way open. But we are kind of working on designing more of a motor driver circuit so that we're not just like pumping unnecessary amps into this thing, driving these motors itself for the entire time. That's it.
Are there opportunities for haptic devices at very small scale?
So for haptic devices in general, or this one in particular?
Yeah, like
And yes, I mean, so like things like vibration, like you can feel vibrations at an extremely small scale. Like your mechanical receptors in your hand are super sensitive to vibrations and things like that. So the fact that you can get this from like a cell phone, for example. Okay. But in terms of like trying to apply this to something like a cell phone, I think it is feasible. There's just kind of a lot of challenges into scaling our device down to that size, not just from the design complexity, but also from the physics. Basically, as you make these cells super small, you have less and less material inside, and it becomes harder and harder to make a really clear transition from soft to rigid when you jam it.
What are some of the design trade-offs with this type of system when you change the stiffness and thickness of the silicon?
Yeah, so I guess it depends what your goals are here. I mean, the advantage of having a thicker silicone layer is that you don't really feel the granules in the material as much. But the downside is if you make the granule material smaller and the silicone thicker, then the kind of the rubberiness and the springiness of the silicone becomes the dominating effect that you feel rather than the jammed material underneath. So if what you're going for is trying to display the most compelling transition between soft and rigid, I think you'd really want to try to minimize that outer layer rather than kind of making it thicker to hide the granules.
I wonder, so some applications, you think transparency would be important, but people like granules
Yeah, definitely. There's actually some interesting work, like Sean here, who has done some work with jamming interfaces before, showing that if you actually use glass beads instead of coffee grounds, and you fill it instead of with air, with something like an oil where you match the index of refraction between the glass bead and the oil, you can create a more transparent medium here rather than coffee.
On a related note, is there any concern that the coffee grounds over time will, become smaller and that?
Yeah, so I guess there is concern on a very long time scale. For the palpation test that I was doing, I was basically pressing into this with like 35 newtons of force, which is much higher than like if you typically press like as a user, and doing that hundreds of times, and I didn't notice too much like variance in the mechanical forces that came out. I'd imagine over thousands of cycles, you would eventually start to grind down. But I guess one advantage of this device is that the silicone and the coffee are extremely cheap, so it's really the electronics and actuators underneath that are expensive to replace. So if you did end up in a situation where thousands and thousands of these cycles kind of ground it down to a point that the granules no longer lock together as rigidly, then you could potentially replace it. Yeah.
And my other question, so in the device where, it's kind of in relation to the medical use and you had the device move around, you kind of talked about one of the limiting factors that I think that you can't get past that it's moving. But would another limiting factor be how quickly the device can change configuration as you're moving?
Yeah, absolutely. Yeah, I mean, as you can see from the videos, like the device dynamics of our device are much slower than say like anesthetic haptic interface. They could run like 1,000 hertz. So device dynamics is definitely going there as well.
Yeah, what is the resolution of the photons that you're able to?
So for the first half of the talk, we were using the first version of Connect, and that resolution was 2 millimeters. Then for the 100-cell array, it's down to 1 millimeter. But so that's the resolution, but there's still quite a bit of noise on top of that.
There's no other questions? Let's thank Andrew.